Hey, Dustin. Okay, so we're back. So page 367, we're doing example 4. It says we're going to factor. We're starting with cotangent cosine squared equals 2 cotangent x. So the thing with solving equations is we can do all of the algebra that we've used before. We're going to subtract 2 cotangent x from both sides, and we can see that we end up with this function right here. I can see both terms have a factor of cotangent x. So we're going to divide that out. We're going to factor that out, and we come up with cotangent x is cosine squared minus 2. After dividing that by cotangent x, we have the 2 left over. So we end up with 2 factors. Zero products property says if 2 functions, 2 numbers, 2 terms multiplied together equal 0, then each of them can equal 0. So we set cotangent x equal to 0, and we set our other factor, cosine squared x minus 2 equal to 0, which gave us cosine squared equals 2 just by adding 2 to both sides, and then we took the square root of both sides. So the cosine of x can equal the square root of 2, and the cotangent of x can equal 0. So we're going to talk about it being in the interval 0 to pi, round brackets on both ends. The cotangent of x has the solution pi over 2. So cotangent, or the inverse of tangent, equals 0 at pi over 2. There's one of our solutions, and the cosine of x equaling positive or negative square root of 2 has no solutions, because positive or negative square root of 2 are outside the range of the cosine function. Because cotangent x has a period of pi, the general form of the solution is obtained by adding multiples of pi to x equals pi halves. So we would get x equals pi halves plus n pi. Adding that on gives us all possibilities for our solution. N is an integer. The graph of y equals cotangent cosine squared x minus 2 cotangent x in dot mode, shown in figure 5.8 of your book on page 367. It confirms the result from the graph. You can see that x-intercepts occur at negative pi halves, 3 pi over 2, 5 pi over 2, and so on. So let's try problem number 41 and come on back to check your solution. So 41 starts with cosine cubed x is equal to cosine x, gathering all the terms on the left-hand side by subtracting cosine x. We can see that we can factor out cosine x, and zero products property says either of those can equal 0. So let's go ahead and set both of them equal to 0. And you can see with our expression here, we're going to add 1 to both sides. So cosine x equals 0. We know x value in the unit circle is 0 at pi halves and 3 pi halves. And we know that cosine x is equal to 1 when x is 0 and pi. So we've got 4 solutions, and then depending on whether we are restricting the domain or not, we know that cosine is repeating every 2 pi, or these values are repeating every pi. So we could say plus n pi, and same thing over here, plus n pi on each one of those solutions. Let's look at example 5. It says we're going to factor an equation of a quadratic type, and we can see that our powers are 2, 1, and 0. So we understand this to be a quadratic function. We're going to take the function and break it into 2 binomials, the 2, -1, and -1 being our key components. I know that 2 sine squared x factors into 2 sine x and sine x. Both first terms yield a product of our first term in our trinomial. And we know that we need to get factors of -1 and factors of 2 that add up to our middle term, -1. So we see in the book it says 2 sine x plus 1, sine x minus 1, and we can see positive sine x for the inside terms and -2 sine x add up to give us that middle term. This all equals 0, of course. We're going to take each one of those factors and set equal to 0 by subtracting 1 on either side of that equation. We get -1, and in the second one, sine x minus 1 equals 0, so sine x would equal 1. Here we do division by 2, and we get sine of x is equal to -1/2. And here we get sine of x is equal to 1. We know that the sine of what value, what radian measure, 7 pi over 6 is equal to -1/2, as well as 11 pi over 6. And for sine of x equaling 1, we know that occurs in one place, and that's at pi halves, or 90 degrees. You guys please try number 49 and come back and check your solutions. So very similar to example 5 that we just did, we see that our first terms in our binomials have to give us a product of 2 sine squared x. So we know that's going to be factors of 2 are just 2 and 1. So sine x times 2 sine x gives us 2 sine squared x. And we know that our last terms, our factors, have to be 1 and 1 because our product is 1. We have to have these add up to 3. So if I have a positive 1 and a positive 2, I know that will give us a positive 3 for our middle term. So we're going to take each of those. 2 sine x equals -1, divide by 2. That gets rid of that guy. We're going to do the same thing over here. Sine of x is equal to -1. Sine of x equals -1/2. We know that that occurs at 7 pi over 6 and 11 pi over 6. And we know that the sine of x gives us a -1 value at 3 pi over 2. 49 said collecting all terms and graphing the new equation using 0 or root feature. You guys can go ahead and graph this and check that we did our algebra correctly. You should see these values for roots. Let's move on to example 6. So the idea here is that we see both sine and cosine function, and that we rewrite it using only one of those. I know you guys do too, that sine squared is the same as 1 minus cosine squared. So if we do that, we can see that now we only have cosine, and we can factor. We're going to go ahead and distribute this. It gives us -2 cosine squared x plus 3 cosine x, and this positive 2 goes out here to combine with the -3 to give us a -1. One way to deal with this is to go ahead and factor out a -1. So we can rewrite this as 2 cosine squared x minus 3 cosine x plus 1. And that's a little bit easier to handle. We multiplied both sides by -1. We're going to factor 2 cosine squared x. We get a 2 cosine x and a cosine x. It's the only way to get our first term. And our last terms have to give us a product of 1. And we have to add up to -3. So you guys can see that both of those operations have to be negative. -1 minus 2 gives us our middle term, -3. We're going to take both of those, 2 cosine x equals 1 dividing by 2. I just did that in some quick steps there. And this one is cosine x equals 1. Well, cosine x equals 1/2. We know that that's going to take place at pi over 3 for cosine x equals 1/2 and 5 pi over 3. And we know that cosine x is equal to 1 at 0. X equals 0. Then we have a period of 2 pi for cosine, so that we know that all solutions would include pi thirds plus 2n pi, 5 pi over 3 plus 2n pi, and 0 plus 2n pi. That's all of our solutions. So in 51, the directions say this, to use a graphing utility. First thing we want to do, though, is get all of our terms on one side of the equation. So we've simplified this. We've subtracted 2 cosine x and subtracted 1, set it equal to 0. And what we want to do then is use our graphing utility to locate those roots. So the first one from the left would be roughly negative 0.861 and then from the right, our reflection across the y-axis. What do you know? At positive 0.861. So that's problem 51, and that's how we're going to use our graphing utilities. So here we're looking at example 7. It says it's not clear how to write it in terms of one function, but we can see that if we square both sides, that's an appropriate thing to do as well. We're going to square this side, square that side. We get cosine squared x plus 2 cosine x plus 1. That's equal to sine squared x. And we can see that now we can turn this completely into terms of cosine. Sine squared is 1 minus cosine squared x. And now we're going to rewrite cosine squared x and gather terms on the same side. So subtracting 1 from both sides, those disappear. Adding cosine squared x to both sides, we get 2 cosine squared x plus 2 cosine x is equal to 0. And we're going to factor out a 2 cosine x. We're left with cosine x plus 1. Again, we're going to take both of those products. 2 times the cosine of x is equal to 0, or cosine x is equal to negative 1. On this side, dividing both sides by 2, we just get cosine x equal to 0. We know that happens at pi halves and 3 pi halves. And cosine x equal to negative 1, we know that happens at pi. Because we're talking about the interval 0 to 2 pi, we are done with these 3 answers and don't have to include all the others. Try number 53, and we'll come back and look at that solution. So cosecant and cotangent, it says to use our graphing utility again, so we're going to go ahead and change cosecant x into 1 over sine x, cotangent into cosine over sine x, and subtract 1. We see that we can now put this into our calculator. Just as we did before, we're going to go ahead and graph this, and we're going to calculate zeros. And by doing that, for problem 53, you can see that x is going to be approximately 1.57 pi halves.